Hello, pre-calc students. Doing intro to limits as a video. So starting off, we're going to understand vocabulary for one-sided limits, and then we're going to go to general limits, and then we're going to go through some examples. So these are the notes. Let's get started. So first off, we have one-sided limits. The limit of f of f as x approaches a value from the left is a left-handed limit. So our notation is going to look like the limit as x, our input variable, approaches c from the left of f of x. So this is as x approaches c from the left. That's what that minus sign means. As x approaches O-A-C-H-E-S approaches c from left. From the left. I need to get better at writing. That says x approaches c from the left. So that's the left-hand side limit, and on the same for the same reasoning, the limit as x approaches c from the right of f of x, so as x approaches c from the right of f of x, that's going to be as x approaches c from right. So as x approaches c from the right. T. And remember, that's as x, an arrow, c from the right. All right, so that's one side of the limits. For general limits, the limit at a point is a function will have a general limit if the function is approaching the same y value from the left and from the right of the x value. So DNE does not exist. So this is just another nomenclature thing. DNE is equal to, that means does not exist. All right. So now that I have the nomenclature down, this is the limit of a point means you're approaching it from the left and the right. And you express this for the notation as the limit as x approaches c of f of x is equal to L. All right. So I want you to consider limits at, think about where there potentially wouldn't be a limit. Consider a hole, a jump, vertical asymptote. So consider at holes, jumps, and vertical asymptotes. Vertical asymptotes. The limit is not going to exist. The limit will not exist. So the limit does not exist. So at a hole, a jump, and vertical asymptote, the limit does not exist. A function is continuous at a point if the limit as x approaches c from the left and the limit as x approaches c from the right are approaching the same y value, and the y value is defined at this y value. So we have conditions. One, f of c is defined. So f of c, so c is what we're going to call the x value, the point that we're approaching. So f of c is defined. Two, the limit exists. Three, the limit of f of x, the limit as for f of x is equal to f of c as x approaches c. So 3, the limit as x approaches c of f of c is equal to, limit as x approaches c of f of x equals f of c. As x approaches c of f of x is going to be equal to f of c. So there we go. And that's just getting our definitions down. All right, so let's look at the analysis of the function. The equation of the function is shown below. This is 3x squared minus 8x minus 3 over x squared minus 9. This is what the function would look like if you plot it out. So, continue. So, using problem 1 continued, we need to factor and simplify. So, factoring out this problem, let's factor out the numerator. So I can see that this can factor into 3x plus 1 and x minus 3. So the numerator can factor into 3x plus 1 and x minus 3. And the denominator can factor as x plus 3, x minus 3. X plus 3, x minus 3. So factoring out, we can cross out the x minus 3, so this will equal to 3x plus 1 over x minus 3. Over x plus 3. So So there's going to be, we're going to have to analyze when x is equal to 3 and negative 3. So when x is equal to plus or minus 3, we might have some issues. Because the function would be undefined at these points. You'd have a vertical asymptote at x equals negative 3 and a hole at x equals positive 3. So we have the coordinates of the hole. Well, we have a hole at x equals 3 because we have a denominator term that would make the function 0 that's canceled out. So that's the hole. That's at x equals 3. So we have a hole at x equals 3. So if we find f of 3, that would be equal to 3 times 3 plus 1 over 3 plus 3. So that would be equal to 9 plus 1 over 3 plus 3. So that would be equal to 10/6. So the coordinates of our hole would be at 3, 10/6. All right, our domain is going to be, let's find the vertical asymptote for find our domain and range. We have a vertical asymptote at x equals negative 3. And we know that because we have a denominator term where this cannot equal 0. All right, so if we have x equals negative 3, that makes the denominator 0, and it doesn't cancel out, so it's a vertical asymptote. We also have a horizontal asymptote at y equals 3. And if you think about it, a horizontal asymptote is an infinite limit. And the whole idea with infinite limits is that as x gets really big or really small, imagine x becomes infinity. The 1 and the 3 get canceled out. So you have 3 infinity over infinity, that's going to approach 3. Or 3 times negative infinity over negative infinity. Negative divided by negative is a positive. So that's also going to get you 3 over 3 divided by 1 becomes 3. All right, so our domain is going to be from negative infinity to negative 3 union negative 3 to 3 union 3 to infinity. And our range will be from negative infinity to 10/6. Remember 10/6? That probably would simplify to 5/3. So let's keep these negative infinity to 5/3 because we have a hole there. Union. Then five thirds to 3 union, and that's because we have our horizontal asymptote at 3, and then union 3 to infinity. So you can also look at this just by looking at the graph, seeing why the domain and the range are where they are. That being said, let's scroll down and look at understanding limit notation. So we have some pre-calculus notation and some calculus notation that we've been exposed to before. As x approaches negative infinity, the graph of f of x approaches 3. The calculus notation here is the limit Hello. Well, the limit as x approaches negative infinity of f of x is equal to 3. So what this allows us to do is have an equal sign here. As I was just saying, as x approaches negative infinity, f of x approaches 3. We can say the limit as x approaches negative infinity of f of x is equal to 3. And this equal sign is what is important. As x approaches infinity, the graph of f of x approaches 3. The limit as x approaches infinity is going to be of f of x is equal to 3. These are, when you're approaching negative infinity and infinity, these are infinite limits. These are also horizontal asymptotes. So these are horizontal asymptotes. A-S, asymptote. You can fit asymptotes in there. Good for you. You have better handwriting than I do. As x approaches negative 3 from the left, the graph of f of x approaches infinity. And the x approaches negative 3 from the right, the graph of x approaches negative infinity. So this is going to be limit as x approaches negative 3 from the left of f of x is equal to infinity. And this says the limit as x approaches negative 3 from the right of f of x is equal to negative infinity. Those are horizontal asymptotes. These are vertical asymptotes. And as x approaches 3 from the left, the graph of f of x approaches 5/3. And as x approaches 3 from the right, the graph of x approaches 5/3. So just some more examples. The limit as x approaches 3 from the left, f of x is equal to 5/3, and the limit as x approaches 3 from the right of f of x is equal to 5/3. Yes? You know it? Alright, I'll be up with that.
Okay, thank you.
It's going to be equal to 5/3, and this indicates the same whole. Alright. So That's a full analysis of that problem. Example 1. Transferring over from pre-calculus notation to calculus notation, which uses limits. Can you explain what the value of a limit represents in terms of the graph? So let me just get a definition for you. The limit is the y value that the graph is approaching from both the left side and the right side. The graph is approaching from both the left side and the right side. Of the, and I'm going to use a quote here, of the target value. And the target value is x equals c. The limit can occur at a hole. Which is, the hole is a removable discontinuity. A removable discontinuity. Right. So that's explaining. Let's do analysis of limit set tables. Let's complete the tables below for the function. Analyze behavior at each value. And remember, this is the same value. What we can do is Here, get our calculator. Put in the function 3x squared minus 8x minus 3 divided by x squared minus 9. Let's evaluate the function at table set. New table start, negative 3.1. So that's going to be at negative 3.1. We should have a value at, let's our function is 3x squared minus 8x minus 3 divided by, we need a parentheses here, divided by x squared minus 9, close parentheses, second table. Here we go. So negative 3.1, we'll have 83. At negative 3.01, you will have 803. Think about plugging in to actually find these. At negative 3.001, you will have 8,003. At negative 3, we'll just look at negative 3 here. Does not exist. Think about what would happen if you divide by negative 3 here. What's 3 squared? Divide by 0. DNE. Then you have negative 2.9999. Negative 2.999. That's going to be negative 7,997. Negative 2.99. It's going to be negative 797. And hopefully you're seeing the pattern here. This would be negative 77. And so you see, this is, if you really look at it, look back at the graph at the beginning of the first page. And what's happening as you're approaching negative 3 from the left and the right. So limit as x approaches negative 3 from the left is going to be equal to infinity, and limit as x approaches negative 3 from the right is going to equal negative infinity. So you see a numerical example. Look at page 1 for this function for the graphical example. You can really see what happens as you're approaching negative 3 from the left and the right. So next we need to explain how this value is related to the graph of the function. So let's think about it. As x approaches negative 3 from the left, y increases. As x approaches -3 from the right, y decreases. All right, so therefore, x equals -3 is a vertical asymptote of f of x. So we have, and this is another example where, and let's look at, you could also plug these into your calculator. You can do it for yourself. I've already done them. But this is 3.008, 3.016. So we can notice how as x becomes a larger negative number, you're approaching 3. 3.082, 2.922, 2.984, and 2.992. In each instance, the limit as x approaches -infinity is going to approach 3. And one trick you can do, if you have this function in your calculator, is that you can see what you're approaching when you have the function in your calculator, right? And you say, let's approach a really big number. It can be even bigger than 1,000. Let's do table start at 10. 1, 2, 3. At 10,000, you're really getting approach to 3. Hopefully, you're starting to see that it's approaching 3. -10,000. 1, 2, 3. It's approaching 3. And looking at this function right here, think about it. As x approaches infinity, you're going to have 3 infinity on the numerator, infinity on the denominator. Everything else is going to become not relevant. And so 3 infinity over 1 infinity just becomes 3. Clear annotations? Explain how this value is related to the graph of the function. As x approaches infinity, y gets extremely close to 3. As x approaches -infinity, y gets extremely close to 3. Therefore, y equals 3 is a horizontal asymptote of f of x. Limits that do not exist. So let's look at limits that do not exist visually. Using the graph of the piecewise function, show below to find each limit, to find the limits if possible, okay? So limit as x approaches negative 2. X approaches negative 2 right here. You can see as x approaches negative 2, it looks like the function's going fine right here. F of x is going to be equal to, oh, I'm sorry, not negative 2. As x approaches 2 from the left, f of x is going to be equal to 4, because coming from the left, f of x looks like it's going to be equal to 4. Limit as f of x approaches 2 from the right, now coming from the right side, f of x is also still good, the limit is still going to be equal to 4 because we're approaching 4. But f of 2, because we have a hole here, is going to be negative 2. Right? Because f of 2 is negative 2, even though the limit as we're approaching from the left and the right is 4. So the limit as x approaches 2 of f of x is equal to 4. So as long as the limit from the left and the limit from the right equal each other, that's the limit of the function. So these are the same, so therefore the general limit, because the limits from the left and the right are the same, the general limit is also true. That was the first problem, example 3. Let's go on to the next problem. The limit as x approaches negative 1, that's going to be, sorry, once again, let me reread this. Limit as x approaches 1 from the left. Well, from the left, function is approaching 3. From the right, as x approaches 1, function is approaching 1. F of 1, however, we have a hole here and a hole here and a filled in dot here. So f of 1 is going to be equal to 1. Limit as x approaches 1, however, does not exist because these values do not equal each other. Not the same, so from the left and from the right are not the same. Therefore, the limit does not exist. Looking at the next problem. The limit as x approaches 2 from the left. From the left, as we approach 2, it's going to equal infinity from the left. And from the right, the limit is also approaching infinity. F of 2, however, does not exist because we have an asymptote at 2. Over the limit as x approaches 2, f of x is equal to infinity or does not exist. And so let's do an explanation here because I want to explain this conceptually. All right, so in this case, I would just say go with infinity, and this is just because the function is unbounded. Clear annotations. Let's move on. Finding limits graphically. All right, use the graph of the piecewise function to find each limit. If the limit does not exist, state why. So note here, the slope is equal to negative 1/3. We'll get here in a second. Limit as x approaches 3. Well, from the left it's 1, and from the right it's 1, so there's no issue here, so it should just be 1. The limit as x approaches 1 from the left. Once again, as we approach 1 from the left, that's going to be equal to negative 3. As we approach negative 2, negative 2 from the left is going to be negative 2. Negative 2 from the right is going to be negative 2 because we're approaching this point right here. So that means the limit as f of x approaches negative 2 is going to be negative 2. Limit as f of negative 2, however, is this value right here, which is 3, because the shaded dot is right here. Limit as x approaches infinity of f of x, as x approaches infinity. So we're looking in this direction. Function is going upwards in that way, so f of x is going to equal infinity. Limit as x approaches 1 from the right is going to equal negative 1, because coming from the right, as x approaches 1, the function will equal negative 1. F of 1 is this filled in dot here, which is negative 3. The limit as x approaches 2 of f of x is going to be 0, because as x approaches 2 from both the left and the right, f of x is going to equal 0. As x approaches 5, we can see right here, extrapolate this line, that f of x is going to approach 3. As x approaches negative infinity, this function is going upwards in this direction. It's negative. So therefore, f of x is going to equal infinity. As x approaches negative 5, f of x is going to approach negative 1. and just looking at the slope here. 1, 1, 2, 3, 1, 1, 2, 3. Yes, as x approaches -5, fx is going to approach -1. And as x approaches 0, it's going to take some algebra here. So 0 is right here. We have a slope of, so for m, so for problem m, we have a slope of our rise is 1, our run is -3, so the slope of -1/3. A point is 1, -3. So if a point at, of 1, -3, our equation is going to be y plus 3 is equal to -1/3 x minus 1. X is equal to 0. So, sorry, y, so remember this is coming from y minus y1 is equal to m times x minus x1. This will be y is equal to -1/3 times x minus 1 minus 3. This will become y is equal to, so y plus 3 equals 1/3 x minus 1. And remember, we're looking at when x is approaching 0. So when x equals 0, y is going to be equal to 1/3 minus 3. One-third minus 3. So y would be equal to 1/3 minus 9/3, which would be equal to -8/3. So that's m, -8/3. All right, the existence of a limit. So the limit as x approaches c is equal to L if and only if the right-hand limit and the left-hand limit exists and they are equal to L, where L is a real number. For example 5, based on what you've seen so far, f of a needs to be defined in order for a limit to exist. Sketch 2 different questions where f of a is not defined. One graph showing how the limit exists, and one showing how the limit does not exist. Explain your reasoning. So the limit of f of x exists. Well, let me get a full view here. So the first one, the limit as x approaches c of f of x exists. So let's have our point C. We have our function, just could be any function, but we have a hole here. The explanation here is that f of C is not defined x is a point discontinuity at x equals C. So even though there's a hole at x equals C, the limit as x approaches C from the left of f of x is equal to the limit as x approaches C from the right of f of x. Therefore, the limit as x approaches C of f of x exists. Limit as x approaches C of f of x does not exist. So let's now show a limit. The limit as x approaches C of f of x does not exist. So we are going to have C here. Alright, so f of C is not defined. This is a function now where, so even though f of C is not defined, the limit as x approaches C of f of x from the left does not equal the limit as x approaches C from the right of f of x. So therefore, the limit as x approaches C of f of x does not exist. Alright, so that's limits, introduction to limits. And we're